Hi, welcome back. Here we have a view of the underside again of this radio with the spotted fever in place. The capacitors are done. And that means that the entire radio is done because I've gone through every section and replaced any caps that were defective, which means all of them that showed leakage. That was all those film caps, or rather paper caps. They were all pretty bad, and so I just replaced them all. I did tests on quite a few of them, but as expected, there were no surprises. The resistors all proved to be very much within spec, some of them amazingly so. And this is again the second time or third time I've noticed this with the Graetz radios. The resistors are very, very good value. They obviously used some pretty good quality stuff back then. These electrolytic capacitors were reformed and they turned out pretty well, so I didn't have to replace them, which is great because I like the look of them. And some of these ceramics were fine. That one there, that dog bone type capacitor's fine as well. So a lot of them didn't need to be replaced except for the paper ones. And the radio is done. And what I'm going to do now is just go through the schematic and basically give you a bit of an outline of each of the sections and any of the discoveries made along the way. So let's get on to that. As you can see, this thing is pretty much colored. This is what I do is I go through each component and each connection after I've checked everything thoroughly. I paint it up, and the ones that are in green is where everything is fine. The blues are capacitors that I've changed. The whites are the ones I haven't touched, like the FM can. I'm kind of afraid of those things. They can give you a lot of headache if you mess with them, and this one is really, really good on FM, so I left it at that. Here we have a bit of an anomaly. This switching had no labeling on it, so I ended up labeling it myself, D12, 11 and 10. That's according to that chart over there. And I found another one that was a bit iffy. That one over there. Where is he? Yeah, that guy over there. That says F1, 2 and 3. That's actually E1, 2 and 3. Mistake on the schematic. And there's another one here somewhere. The F1, 2 and 3 was labeled, I believe, as E1, 2 and 3. So going through this, you actually end up correcting some of the mistakes on the schematic, which is not unusual. You do find them, and you have to be on the lookout for the mistakes, not take everything as gospel, because these guys did make mistakes back then. Whether they did it on purpose or not, I'm not sure, but you do have to be careful. So there we go, the whole thing is painted, and so it's done. I still have not put in those two capacitors. I'm waiting for them to arrive. Those are the filter caps across the mains line. This thing works perfectly well without them. There's no real risk, so I'm not too worried about that for now. So let me take this out of this plastic sheet and show you what the circuit does. So here's where everything starts. You have your antenna signal, your signal comes in. There's the ground connection on the back of the radio. It comes in through a filter, and before the filter is a switch. Now this took me a while to figure out because it doesn't actually tell you what switch it is, but after a little bit of searching, I found that this is the switch that is actually activated when you rotate the ferrite core with using that dial on the front of the radio. When you activate the ferrite core, it switches off, rather closes the switch so that your antenna signal gets shorted to ground, and you have no antenna signal coming into the radio. What it does then is it activates this switch here as well, which lets your input come from, or rather your signal come from your ferrite antenna, which is over here. So you're either using the ferrite antenna as a signal source, and it's also selected with that switch over there, or you're using the external antenna when this one is open. So if you have an external antenna signal coming in, that coil over there in that circuit allows you to actually cut out any frequencies around the IF frequency. So when you align the radio, one of the steps that you should do is to feed a IF frequency in here, 472 kilohertz, with a audio signal modulated on top, and you set up the level till you hear it on the speaker, and then you tune this till you hear it as low as possible. So you minimize the IF coming through there. It's an IF trap. Okay. Signal then comes in and it gets fed through to this coil over here, which then provides a signal on the output here, and you then get the signal coming through here to that point over there on that switch, so F7. That then effectively is your AM input to the mixer tube. The top part comes from the FM section, that signal through there, and that is your FM signal that's going to go into your mixer tube. So mixer preamplifier tube, effectively. So you choose with this switch whether you're using FM or AM. Once the signal gets in there, it's ready to be mixed with the local oscillator signal, which is provided by this part of the circuit. Now, this part of the circuit, it's pretty standard for most of these radios. A few things you notice here: the actual local oscillator frequency goes into pin 9 of this tube, and it gets shorted to ground with F5 and F6 when you choose FM. So when you choose FM, your local oscillator effectively is not feeding a signal into that tube. It's shorted to ground. Otherwise, your local oscillator is producing your local oscillator frequency, your basically the frequency that you're going to use to mix with your input signal. It'll be the input signal plus the IF frequency, and the band of frequencies you can select depending on whether you're listening to AM on long wave, medium wave, or short wave. And that's what these switches are here for. They short out part of the coils, activate others, so that your frequency band is selected to feed into your tube, into your mixer tube. Now, the mixed signal, obviously this triad over here is part of the feedback, the positive feedback that creates the oscillation. The mixed signal comes out, the IF signal comes out over here. Over here you've got your input frequency, your local oscillator frequency, the sum of the two and the difference of the two. And it's the difference of the two that you want. But at the moment, when it comes out of here, you've got all of them. And they go into this IF transformer. Now, we're looking at AM, so that's the lower section. It's these two coils over here. These two coils over here are where you select, you tune them so that only the IF frequency gets through with the modulated signal on top. And that's basically your first IF transformer. The top section is the IF transformer for the FM. Now there's one thing here that's slightly different to what I'm used to, and that is this feedback coming out here. It's basically coming out of this, this is basically your signal coming out here through a 10 nanofarad capacitor, which goes to a point K. And point K is down here, and down here is straight to the cathode of this tube. Now, there is a tunable coil over here, which I haven't touched, by the way, in parallel with a capacitor. So you've got a tank circuit over here, and I'm not absolutely certain what the purpose of this is, but my guess is that it has to do with the bandwidth of your signal that's getting through. So this will have some effect on improving the quality of the signal that goes through in a feedback format. because this part of the circuit actually biases the tube. Okay, now you've got the usual things coming into this grid over here. There's that 1 meg resistor over there. That comes from the AVC line. AVC line, the best point to identify it is this A2 over here, which we'll need to refer to later. So that's your AVC signal. The more negative it is, the more it cuts off this tube, reduces the signal level, so it basically stabilizes the level of your output depending on whether the station is very strong or not. Right, once the signal gets to there, it's now into the IF section, the IF path of the radio. The FM uses this dipole antenna. There's an internal dipole in the radio, but you can also connect one externally. There's actually a tap in the middle, and there's a 30 ohm resistor which goes down here and goes to the external antenna, the wire antenna for the AM. I'm not absolutely certain whether this is supposed to provide a signal from this internal dipole to the AM, or whether the external AM antenna is supposed to provide a signal to the FM. But either way, they're linked. The signal comes through this tunable section here, and this is acting as an RF amplifier. Amplifies the signal, which then goes into, I was going to say the little black box, but it's not, it's a little metal box. And this one I have not touched. The FM on this radio is exceptionally good. I didn't want to tempt fate by messing around with it. I've had enough of a headache on the last radio. And having been fortunate enough to find one that's got brilliant FM, and I mean really good, I decided to leave it exactly as it is. There are no paper caps in here. I believe the resistors will be fine. The coils are usually fine. And the result is good, so I let sleeping dogs lie. The output of this section comes through here and goes to that switch into the mixer tube. So once you get through this tube, you have your signal coming through here. In one case, in the FM case, you have the FM modulated signal coming through and being tuned by these two coils over here, this transformer. In the AM, you have your AM IF frequency coming in with the signal superimposed with amplitude modulation that gets passed through these two coils, this transformer here. And those two then become the input to this EF41 IF amplifier valve. So once your signal comes in here, these parts are, this section here, the screen voltage, I believe it's called a variable mu. This is basically to establish the gain of this tube. It's biased from the B+, the second B+ over here through a 200k resistor. There's some filtering to ground. The cathode is grounded. So this is a self-biasing, basically creating the negative bias on the grid. I don't see any biasing happening over here. Well, maybe. Yeah, there it is. There's actually a bias voltage, and it's also coming off the AVC line. That's the AVC voltage over there. It comes up here, up there, through a 200k resistor, through that coil, and to your grid. So again, the AVC is affecting the gain of this coil, of this tube. So once it comes out of here, it again goes to another IF transformer can with the FM section at the top, with, in this case, the center tapped output secondary of that transformer, where your FM signal then goes to the two diodes, and you get your discriminator there. And the bottom section is the AM. There's the primary, there's the secondary. Your signal comes out of here. There it's producing your, over here, this 2 meg resistor goes to here to create the IF, the AVC voltage. The output of that signal, of that coil, of that transformer, is the bottom line over here. It comes across, and into that diode over there. So that's where your detection happens. And the FM detection is using these two diodes over here, and that's producing that voltage across that capacitor that we use to measure, to align FM. That's the electrolytic capacitor, 5 microfarads. This is the one that's usually put in with supposedly reverse polarity. The positive is grounded, the negative is connected to that point over there. There's actually a 1K trim pot over here, which in this case was actually set to 500 ohms. And I presume that's to do with part of the FM alignment as well. The audio signal that comes out then goes through. The audio signal comes out through there, and it ends up being through the switching network here between FM and AM. It then becomes your audio signal that comes out the bottom here through this 10 nanofarad resistor that goes to the selector switch. Now this selector switch we saw before, that's where you selected between radio and pickup. So your AF, your audio frequency, ends up coming out here. So that's basically it, very, very simply. I'm sure there are things here that have not been explained 100% correctly. Each of these radios is different. Each time you do one of these, you learn something new. In this case, something I did learn was that, I will get to that in a minute, but it has to do with the alignment of the AM. They have a rather more complicated suggestion for the alignment. I decided to not follow the suggestion for the simple reason that understanding the German was a little bit difficult. But basically, alignment is pretty much alignment, especially when you talk about AM. You are aligning the IF transformers, in this case this transformer and that transformer, and you're aligning them so you get the best possible signal coming through on the IF frequency, and as close as possible to the IF frequency. So that's basically a short description of the circuit. Don't take this all as gospel. As I said, some of this is not described perhaps textbook fashion, but it's the way I understand it, and it's worked for me so far. Let's have a look at the back of the, or rather the part of the diagram that shows all the coils. For a one-page bit of documentation, this thing is pretty complete. And that's pretty usual for these radios, because you'd usually get one schematic sheet. There are usually other pages, and I do have them. But if you look at the schematic, if you have the schematic, you sometimes don't need all this other stuff. And I say stuff because, unfortunately, it's very difficult for me to understand. I don't understand German. I have to go by the pictures, and some of it is self-explanatory, but this part of it here describes exactly where your coils are, looking from the back. This is your first IF transformer for AM, coil 76, 77. This is your first FM IF transformer, 70 and 71. This L1 here is your IF trap, the one where you tune for a minimum signal coming out. This is where it stops the IF frequencies from going into the antenna. Here you have the second IF transformer. Again, this is the AM, this is the FM. And then they have 2 points at the back here that you can use to do the FM alignment with a null meter and null microammeter and so on, if you decide to do that, which I have not done. Also on the FM section, you've got all the coils and your tuning capacitors, which allow you to do the alignment for the IF, both RF, and you have your first IF transformer is also here. It's coil 28 and 29. So you'd align that for the best reception or the best pass-through of the 10.7 megahertz IF. There are a few other things over here, for example. So Ablagepunkte here, I presume, are checkpoints. It tells you that medium wave is 600 and 1440. My guess is that that's where you adjust the RF alignments for. I'm sure that the full instructions here will tell us more clearly, And yes, it does. Exactly right. 600, 1440. And so this is repeated in the other sheet that I've just put aside. Long wave, you adjust for 200 kilohertz on the scale, and short wave for 7 megahertz on the scale, FM for 88.5, 93, and 98. And it also then tells you, helpfully, the IF frequencies. For AM is 472, and for FM 10.7. So that's basically it on the paper side. And let me show you now a little bit about the IF alignment of this radio. Bearing in mind that this is upside down, it's fairly easy to find from that sketch that I showed you earlier where the transformers are. The first one, or rather the last IF transformer for the AM, is over here with one coil on the bottom and the other one at the top. The first one is over here with this coil and that coil, both of these for AM. The FM sections are these two over here, and in this particular case, this one over here. So to set the IF alignment to this, I'm not going to do it on camera for the simple reason that I did it, lost the video, and it would be a bit of a fake doing it again. But I'll describe very carefully what it is that I did. And it's fairly normal. From the signal generator, I produced a 472 kilohertz signal with a superimposed audio signal on top, 400 hertz or 500 hertz, I think it was, 30% modulation. That goes into the mixer over here. So that goes into pin 2, which is the grid of the mixer, and then you are ready to do your testing. You do this through a 5 nanofarad capacitor, 4.7 nanofarad capacitor. Be very careful, you can slip here. Everything is pretty tightly wound together, so if you're not careful over here, you can actually short everything out and probably mess up your signal generator to boot. So your signal goes in there, and then you are doing the testing for the levels in one of two ways. One way is to actually put a voltmeter, a AC voltmeter, millivoltmeter, across the speaker. The other way is to measure the level of the AVC voltage, which is the one I opted for, and it's the one I prefer. And this one has a very handy position where you can actually get the AVC voltage, and that is that pin over there. That is A2, which I mentioned earlier. You just clip your meter on there, and that gives you AVC voltage. And it starts off at about minus 0.5 negative. And when it finds a station, it will go to a higher voltage negative, as low as, or as high negative as minus 6 volts. So what you do is you set your signal coming in, you measure the AVC voltage, and it gives you a reflection of the strength of the signal. So when you tune your coils, it gives you a measure of the strength of the signal getting through, and because what you're passing through is your IF frequency with a modulation on it, the higher the voltage is there, negative, the more you're getting through. So you basically adjust for a maximum negative voltage, and that tells you you've aligned the coils. Much easier to do. It also avoids having to have your speaker on and either blowing your eardrums or irritating yourself and your family, because you have to have the speaker on to measure its voltage. You could put a dummy load on there, but usually you just use a speaker. So I prefer to use the AVC voltage, and in this case, that's exactly what I did. Then I did the tuning of those two capacitors, or the two transformers, as I mentioned, and the result was not that much of an improvement. I would say, obviously I didn't keep a record from beginning to end, but I would say not more than a 10% improvement on the level. And that's not that much really. I mean, 10% of the voltage is a very small amount of dBs, believe me. So I wouldn't even think that it'd be noticeable on the output. There was nothing dramatic. There were no dramatic jumps or dips. So I think overall, this is a pretty boring stage on this radio. The only excitement, and it's not a very positive thing, is that the wax they used on here was incredibly dry. They put wax on the cores to stop you messing around with it inadvertently. And you can just see that there, I think. That there was waxed completely closed, which is usual. But in this case, it was very, very dry wax. Now, I've had cases where it's very simple to take the wax off. You just scrape it out very gently and everything comes off pretty well. This is not one of them. I was actually quite worried that I was going to damage the coils by putting too much pressure on there. I used a wooden toothpick, like a toothpick. Basically started chipping away very carefully. It took me about 3 times as long to clear the cores, to clear the cores of wax than it did to actually align the thing. So there we go. What I do want to show you is I want to show you what sort of alignment we've actually got. Now what I'm going to do is I'm going to measure the voltage there, the AVC voltage. I'm going to put in an IF signal, a 472 kilohertz modulated signal in there. We're going to measure the voltage, and I'm going to actually tune the signal generator off the IF frequency, both lower and higher. And what we should see is the peak of that tuning. Now the reason I'm doing this is for my own peace of mind. At one stage during this alignment, I aligned it with the speaker first, just to try it out. I have a new dummy load that I've built, so I wanted to try the dummy load. So I basically tried it with the AF signal, and I did the alignment, and then when I played with the signal generator, I found that the actual peak was at 471 kilohertz, which was actually 471.4 kilohertz. So it was 600 kilohertz, 600 hertz away from the actual alignment, the actual IF frequency, and I couldn't understand why. I went back and did it again and peaked it at the IF frequency, and when I measured the signal going in and detuned or tuned away from the IF frequency, I found again that the peak was not at the 472 but at 471.4 kilohertz. And I couldn't for the life of me understand why, and quite honestly I still don't fully understand why, because when you align it, you align it. That's my logic. What I did find, and perhaps that is the reason, this particular coil here, the second time around, I found the other peak. So what this is a core. You've got a core with a coil wound around it. And the alignment is done by moving the ferrite core in and out of that coil that's wound around it. So if you've got this thing in the center and you move it backwards, you unscrew it, you're moving it away from, basically you're reducing the amount of inductance because you're moving the core away from the coil, and that has obviously an effect on the interaction of the transformer. If you push it beyond the center and you're going out the other side, when you're equally away from the center, you're basically creating the same amount of inductance, except in the other direction. And I found that the second way, on the second peak, I didn't get that problem. I didn't get that peaking at a frequency lower than the IF frequency that I peaked it for. So there must be an explanation for this. Quite honestly, I don't have it. I'm sure somebody out there knows this and probably laughs their head off when they hear me say this, but there is some explanation. One day I'll find it, share it with you. But at the moment, that's what I got. I just want to measure the peaks and just see how tight that tuning is. The idea is with these radios, medium wave here in Madeira it's forget it. There's like one station and there's another 1 or 2 from the Canary Islands that I can pick up. Long wave, I get one station from France in the evenings sometimes, which you can't really listen to because it's really crappy quality. FM is fantastic, which is what I really do this for. And these radios then get used almost daily. At least one of them is used daily to listen to FM. The other thing that's interesting to listen to sometimes is shortwave. And shortwave is very lively. I'm in the middle of the ocean here. So it is pretty lively. And shortwave, what you really want is a very tight tuning. You want to be able to increase the sensitivity between stations that are very close to each other very, very accurately. So you want to tune the IF stages as sharply as possible, so that when you're getting one station, you're not actually overlapping with the signal from the one adjacent to it, which might be just a few kilohertz away. So I want a very tightly tuned circuit. What these guys probably wanted back then was, on certain stations, they were transmitting music. And with music, you really want a wider bandwidth. You want to get the quality of the signal coming through more accurately. So in that case, you'd want the hump of the tuning of the filters to have a flat section at the top, probably about 5-10 kilohertz wide, so you can actually get a bigger bandwidth of signal, of music signal coming through. That's not the case here, which is why I didn't bother too much with some of the descriptions they had here, albeit in German. But I got the idea that they were basically warning you to be careful about not reducing not sharpening the tuning too much, or you'd lose fidelity on your AM stations, which is a bit of a joke. But in those days it wasn't. That's what they had to live with. And I suppose these radios making some provision for that was actually quite a feat of engineering. Right, let's get on to the next thing. So here's our setup for this little experiment, which I found has another surprise in store for me. Let me show you what I've got. We've got the signal generator producing a carrier at 472 kilohertz, which is the IF frequency, and it's modulated 30% modulation with a signal of 400 hertz. That comes through and is connected to through a 10 nanofarad capacitor, through a 5 microfarad, take that again. It's connected through a 5 nanofarad capacitor to what is effectively pin 2, the grid of the mixer tube. I've actually connected to the small capacitor before it, it's not a problem. I then am measuring the AVC voltage at that pin A2 that I mentioned earlier. And what we have at the moment is minus 3.3 volts. You can actually hear the signal. I've turned the volume down low. I could turn it completely off if I wanted to, but you can hear the signal. It's not loud, but it's there. So let me show you what happens when I tune out of that frequency, out of the IF frequency. So what I'm doing now is I've set this thing to 460 kilohertz. It has the modulation on it, and I'm reading the AVC voltage, which here is minus 0.53 or so. Now I'm going to increase this in 1 kilohertz steps closer to the IF, and we'll see what happens to the AVC voltage. So here we go, 460, 61, 62, or 4, 5, 6, 7, it's still there, 8. So let's see what happens when we start at 460 kilohertz. We've got a 462 kilohertz carrier with the modulation superimposed on it, and we are reading a minus 0.53 volts AVC voltage. So I'm going to up this in 1 kilohertz steps, and we'll keep an eye on the voltmeter. Let's go. 3, 65, 66. It's just jumping up 1/100 of a volt. 67, 68. Now it's starting to come up, or 69 rather. 68, 69, 70. That was quite a leap. 71, a bigger leap. 72. There's our IF frequency, minus 3.3 volts. That is what I peaked it to And believe me, it's peaked exactly. Using both methods, this has been peaked. Using both the AF method and the AVC voltage method, that is peaked exactly to 472. Now watch what happens when I go beyond that. 472 IF frequency, here's 473. It's actually slightly higher. Here's 474. It's still a bit higher. 75, you're back to 3.3. 76, we start dropping, minus 2.5. 77, minus 1.3. 78, 79, 80, 81, 82. We're back to the minus 0.53, 0.54 that we started off when we started off at 10 kilohertz below. So what we see here is actually a hump. We have a 3 kilohertz or so hump just beyond the IF frequency. Let's go back there. Let's see that. There, 475, 3.28, that's where about the peak value. 74, slightly higher, or 73, 72. And there we start to drop again. So from the IF frequency and beyond another 3 kilohertz, we have basically a flat section. Now that was something I wasn't expecting. My guess is that that is your bandwidth of your AM reception. If we go to the minus 3 dB point, and we'll do a little chart and see what that comes out at, we will get the bandwidth of that of the IF filters. And that leaves me in a quandary, because my understanding of it is that you tuned exactly to the IF frequency, and then the bandwidth was sort of spread a little bit to either side. And now I'm basically going to have to go back to radio theory and figure out why this happens. And if you recall, I mentioned earlier that when I had the coil, the first IF coil, in the opposite direction, in other words, almost out as opposed to almost in, fully in, I had that exactly that difference in frequency, but below the IF, not above the IF. So it seems to be a bandwidth for your signal. Until I get a better explanation, that's the one I'm sticking to. Right, let's have a look at the chart. Here's our chart, or here's our graphic display of the filters bandpass, and it becomes pretty clear what's going on here. And it actually is very uniform as far as a bandpass filter goes. What we actually have here is the baseline, which is that 0.5455 volts negative. Obviously this scale here is negative voltage. So that one there is actually -1, -2, -3, -4. That's giving us an indication of the strength of the signal. Over here at the bottom we've got the frequency in kilohertz. We started at 460 and we went up to 482 over here. And then I plotted the values, frequency versus the voltage measured across that on the AVC line. And this is what we get. Pretty smooth transition, climb, section that's flat, more or less flat over here, and down again. Very nice curve. It's uniform on both sides, almost textbook, and with a little bit of help from the extrapolation of this spreadsheet program, we get this looking like a textbook curve with a 3 kilohertz flat section at the top here. So on the IF frequency of 472, we do indeed have a peak, right? Here's the 472, this red line, the vertical red line going here. And then we get it flattening out to another little peak. Now, this is in volts. If you work this in dB, this difference between that little peak there and that bottom section there would be practically 0 dB. 0.1 dB, 0.2 dB, whatever it is. I haven't worked it out. But what we see here is we've got a curve with a 3 dB curve marked in here. This green one, that's where 3 dB works out relative to that peak. And we see that we indeed have a 5.6 approximately between that frequency there and that frequency there, where it crosses the 3 dB point. We've got a 5.6 kilohertz bandwidth over there. Now, obviously, some of it is above the line, some of it or above the IF frequency, some of it's below the IF frequency. And as I said, I'm not quite sure how the signal gets passed through, whether it's, you know, on one of the sides or both of the sides or whatever. I expected something different. I would have expected something like that, you know, with the IF frequency straight in the middle and an equal amount to the left, an equal amount to the right. I would imagine, from my understanding of it, that the amount below and the amount above would be the same. So in other words, the signal that's going through, in this case, it would be in this part here, is duplicated in an inverse format on the lower end. So in effect, you'd probably be wasting half the power. I don't know if this really makes sense. I know that this here, the way we have it, almost looks like sort of an upper sideband transmission. I know it doesn't make sense. It doesn't make sense at all to me, but I'm sure there's an explanation for it. It works too consistently to be a fluke. As I said, I did this with that curve on the other side. I actually got this section below the IF frequency, and the flat section was approximately the same. So I'm sure this is intentional. I'm sure there's some basic radio theory that I'm forgetting here. I'm going to feel really stupid when I find out, but hey, that's what I found. That's what it is. Right. That's our bit of theory for now. We've got the radio completed. There may be one or two little things I want to do, but I'll keep that for the next one, which will be the last, I presume, the last video in the series, where I will tackle the cabinet, which has a couple of challenges, nothing too serious, and then we'll be able to have a look at the final complete mounted radio. Right, thanks for watching, and see you soon.